everybody. I hope everyone's having a wonderful day. So today we're going to be talking more about amortized analysis. So remember, amortized analysis is a kind of worst case analysis, where what we do is we take a sequence of operations as opposed to just a single operation, which is what we normally do. Remember, the main reason why we're doing this is because when we do analyses on data structures, we oftentimes have certain operations we do, but sometimes we're very pessimistic when we do our analyses. So what we want to do is come up with a bit more of a realistic way of talking about this. So we're going to look at a sequence of operations. So for example, a sequence of put operations into a dictionary. And what we do is we consider the worst case running time of each one of those per operation. So naturally what falls out of it is one of the more standard techniques. There's other ones that do exist. I'll mention those later. One is called the aggregate method. So this is where you just take the total cost of all of your operations, so you have n of them, and you just simply take that, the total running time, and you divide it by the number of operations. That's it. So I'm going to first show you a crude way of doing this. So this is kind of like the quick and dirty analysis, and I mean, if the analysis naturally falls out to do it this way, you can totally do that. I'm going to be more particular after this one, because I feel like it's better to see what I want to really illustrate. And I mentioned many times I'm going to illustrate this using the example of doubling the size of the array every time we resize. So I'm going to imagine I have a sorted array dictionary. So an array-based dictionary, or what I'm going to do is I'm going to have an array. And I'm going to imagine I'm going to put in each one, a put operation. Each put operation is going to put an element into my array. You can imagine it's going to be filling in, but as it's doing so, it's sorting them. So it goes in, and if I ever have to do a shuffle, it performs a shuffle and shifts over the appropriate elements. And we do this for the first n operations because there's room in the array to do this. Each one of those takes linear time, right? But on operation n plus 1, which is the one that gets you just outside the bounds of the array, if you attempted to fit it in, the array is going to be too small, so thus it needs to be resized, and we have to perform some copies. We have to copy all the elements, and then we can do the insertion. So doing all those copies takes linear time, right? Then the copying takes linear time. Then the insertion takes linear time. So that n plus 1 operation takes big O of n time. So if I compute t of n, remember that's the worst case time over all the operations, it should be n times n, which is the number of operations. So it's going to be those first n operations. Then my resizing occurs, and that takes linear time as well. So that means that if I take this aggregate method approach, what I do is I just take n times n plus n, and I divide it by the number of operations I've done so far, which is n. And thus, that means that the amortized cost, or the time amortized, is going to be big O of n, because this is going to be n squared on the top in terms of big O, divided by linear term. It's just going to be linear. So if you actually look at this, this actually isn't too bad. So that means that one operation where when we do this, you're going to see that resizing really just doesn't do a whole lot. It's very infrequent. That's the point and message of this amortized analysis. Is that expensive operation, the resizing of the array, does not happen very often. So as far as we're concerned, this takes big O of n amortized. So that's how you'd often say it. It's the time amortized. So or amortized time or amortized cost. Now, you might ask, well, why is it called amortized? Now, anybody that's interested in finance or anything like that, you might think of this more as a managerial kind of position where what you do is you imagine you do a bunch of things. And what you want to do is you want to prolong yourself by avoiding these really expensive operations by doing as many cheap operations as you can. So you can look at amortize as in the average over all of those operations, right? So it's just like if I go to the bank and I take out a loan or something, or I have a student loan or something like that. Normally what I would like to do is I would like to deter the really nasty situation from happening by considering all those other events that preceded it. So does it really pay off? Like if I have a loan, I make little payments so that when I'm required to make that big lump payment, I've already made those small payments in advance, so those together kind of cancel out the expensive one. That's at least one way you can think about this. There's one amortized analysis technique that is basically this. But this is a kind of a quick and dirty way of looking at it. I'm going to show you a more sophisticated way of doing this, which allows you to give more detail. And I'm going to consider the case of doubling the length of an array. Because I've told you that doubling it is a pretty good practice in the past. So I really want to show you that this is indeed the case, using amortized analysis. So we're going to consider an unsorted array dictionary. Let me just switch my marker. While I'm doing that, I just want you to think off the side of your head. Okay, when I did that quick and dirty approach, can you see very quickly how in our heap, insertions take big O log n amortized? Do you see that? What we did was every single time we did an insertion, we did that while we assumed the array was not full, right? But when it became full, we had to resize. We would have to resize the array. But if you look at our analysis over there, it really does not look like it actually hurts us. So you can see that that approach actually works pretty well. You can see how you can take the idea I gave you just before, and you can generalize it to talk about things like heaps and all sorts of other situations. You can also use it in our situation here, but I'm going to be far more careful because I want to show you how you can use this more generally. Okay? So we're going to consider an unsorted array dictionary. So I'm going to be more specific because I was saying a lot of things there. Start with an array of length. So this would be the more formal way of doing this. Start with an array of length 1, which is equals 2 to the power of 0. So we're going to be using this doubling technique, the one that we talked about. So here, what you do, you would resize the array and perform the copy, then do the insertion. Since it's unsorted, you can see very naturally how you could do this, right? You perform the copies, then you would put in the next available spot. So the array will be doubled. Whenever an insertion is attempted when the array is full. So when that insertion occurs, it'll check if the array is full. If it's full and it resizes, then it does the insertion. Okay? So what I mean by this is, imagine I have an array of size 1, and I put an element in here. Okay, if this is full, then what I have to do is I have to double the size of the length of the array, and then I perform my insertion, right? So do you see how every time I'm doubling it, so I'm going to be doubling. Okay, now when I attempt the next insertion, it's full, so I need to double the length of the array, and then I perform my insertion, right? But then I do another insertion. And this one I didn't have to do the copies over, right? However, when I attempt another insertion, then I run out of space, then I need to double the length of the array. Then I would do the insertion, then I would do another insertion, then I would do another insertion, then I would do another insertion. And presumably this would be like the 9th operation here. So this would be where I have my 9th operation. Now, clearly you can see that this is outside here, so this would keep going until we have a length of 16, right? And you can see how this process plays out with this doubling approach. The point is that not every time it's resizing the array. It only does it when it's full. When does that happen? It only happens during a power of 2. So on 9 put operations, you'll see the following. So let me let me make a table here of just basically what I did here. And it will help us derive how we're going to count the operations. So let's look at this. So let's say operation number, and then we're going to have the time it takes and the size of the array. So we have three columns, the operation number, the time, and the size of the array. So we start off when we only have one. Our first operation, it takes one step because the array is of size 1. Remember, when we consider the second operation, then this is going to take 2. It's going to perform, we're going to be counting the insertions and the copies. So keep that in mind. We're going to care about copies and insertions here. So this, for one, takes one cost, and this is going to take one cost per element copied. So if I have to do n copies, then this cost is going to be n. So here, you'll notice that this will double the length of the array, so the size of the array becomes 2. Then what happens is, okay, operation number 3. Then I take 3 steps because it's full again. On the 4th, I will do how many? 1, right? I just put it right in, like I did before. Size of the array is still 4. On operation 5, I take 5 because it's full again. I double. Remember, I'm just doing this process. I'm just writing it out as a table to help me get a little bit of intuition of what's going on. So 6, this should be 1. 7, it should be 1 because it's not full yet, right? 8, it shouldn't be full yet. However, on operation number 9, it's going to take 9 because remember, it's going to have to do 8 copies, then do an insertion. And this now the length will be 16. So do you see the pattern here? You see that there's actually sometimes where we're just going to have a unit cost. Other times we're going to have it where we're actually going to have to perform this copying. But it's becoming more and more infrequent as the length of the array grows. Okay? So what we're going to do is we're going to define the time taken, or cost, C of I, of an operation I as follows. Okay, so I'm going to define the cost of an operation. Now remember, copies, and we have copies and insertions that occur. This is just a table to help us get an idea of what's going on. So I'll start off with the second case, which is very easy. So C of I is going to be this piecewise function, and we're going to have 2 cases. What's the easiest one? It's when, of course, you just do the insertion, right? So it'll have cost 1. When does that happen? It happens when the array isn't full on the insertion, right? So what does that mean? So this is when an insertion happens. So since it takes constant time, I'm going to assign it a cost of 1. Just takes constant time. Keep in mind, it's just some constant that I've assigned it. However, how do we determine when this doesn't happen? By what does happen when it gets full, right? So how much work gets done whenever I have a resize occur? Okay, well, let's look. Every time you'll look at the row for which a resize occurs, and you'll say, okay, well, when operation 3 happens, that's when it's full. You'll see the time is exactly equal to the operation number, right? See that? 5, 5, 9, 9. So the cost is going to be the number of copies plus the insertion. When does that happen? It happens when if I minus 1 is equal to 2 to the power of k for some k greater than or equal to 0. So I'm going to call this case 1, and this is case 2. So this is when you have copies and an insert. So you have copy and an insertion. Case 2 is when you just have the copy. Sorry, the insertion. I'm getting ahead of myself. So the point is that I have my cost here. So this defines the cost of each one of the operations. So naturally, you might ask what T of n is. What's T of n? Well, if I have n operations that occur, then all I'm going to do is I'm going to make a sum. I'm going to count up C0, C of 1, C of 2, C of 3, C of 4, all the way up to C of n. And that's literally T of n. Oh, I hear the train. It's saying it's time. Okay, I want to ask you another question. Now, this is going to be very important. So I said that there's costs associated with each of the operations. I need to know how many times each one of these two occurs. So how many times does this resize, the case 1 occur? Well, it happens, okay, well, to make this a little easier to see, I'm going to use red to help you see. And it'll become a little bit more clear if you think of powers of 2. So it happens when I minus 1 is equal to some power of 2. So that happens when? So it happens when it's 2, right? Because 2 minus 1 is 1, which is 2 to the power of 0, right? It happens when 3 happens because 3 minus 1 is 2, which is 2 to the power of 1. It happens when it's 5 because 4 equals 2 squared, right? It also happens here. How many times does that occur? Well, this is when it was 2 to the power of 0. This is when it was 2 to the power of 1. This is when it's 2 to the power 2 squared, and this is 2 cubed. Those are when the resizes occur. How many times does that happen? It's dependent on the powers of 2. So how many powers of 2 are possible given that number? Now, let me write it down. So case 1 occurs the ceiling of log base 2 of n times as the array is resized whenever, and this is whenever it occurs, I minus 1 is equal to 2 to the power of 0, 2 to the power of 1, 2 squared, all the way, actually, well, 2 cubed here as well. Let's just put it in there. All the way up to 2 to the power of the ceiling of log base 2 of n minus 1, where minus 1 is in the exponent there. Now, you might ask, why is it minus 1? It's because I know that it's going to happen the ceiling of log base 2 of n times. Now, how do you know it's ceiling of log base 2 of n? Okay. Remember, it's I minus 1 as a power of 2. So how many powers of 2 can occur? It's how many times it takes me to divide down to get to 1. How many times is that? That's log base 2 of n. So if I give you the number 8, how many times do I have to divide 8 to get down to 1? It happens 3 times, right? However, this happens whenever I minus 1 is equal to some power of 2. However, what's I? I is always 1 higher than the amount that I'm given. So it means that I have to be somewhat pessimistic with the way I analyze. So notice that when I do this, I always have a bias towards 1 higher than would normally be the powers of 2. So if this was happening when I is equal to 2 to the power of k, it would actually be the floor of log base 2 of n. However, I'm always considering 1 higher, meaning that I need to always round up the logarithm, okay? So if you're not sure about this step, don't worry too much about it. The point is to observe the powers of 2, okay? So that's how many times this occurs. So how many times does case 2 happen then? How many times? Well, if there's n operations, then it's n minus the ceiling of log base 2 of n, right? It happens this many times, right? It has n minus the log base 2 of n, ceiling. And that's how many times it happens. So now let's put this all together, because now I know how to get t of n. The total time taken to perform a sequence of input operations is the following. It's T of n, which is going to be equal to this. Remember, I said it's the sum of all the costs of all my operations. Which is just the sum of all of these. So C1 plus C2 plus C3 all the way up to Cn. Okay? Well, C of n. I can tell I'm getting really excited about this. The payoff is going to be so worth it. Okay? You don't know what's coming. Believe me, it's going to be very, very fun. Okay, so how many times did case 2 happen again? It happened n minus the ceiling of log base 2 of n. So what was the cost in case 2? Well, it was 1, so I have n minus the ceiling of log base 2 of n. So this is case 2 right here. Just showing you where it is. Plus, okay, now remember, every other time is going to be case 1. So remember, the cost for this one was I. But what's I in terms of 2 to the power of k? What is it? So if I have I minus 1 is equal to 2 to the power of k, then you would agree that I is equal to 2 to the power of k plus 1, right? I'm just rearranging this. So I'm going to write this instead in terms of the powers that I observe down here. So these ones right here. So k is going to be representing the exponent in the powers of 2. So I'm going to have the ceiling of log base 2 of n minus 1 up here. And this is going to be 2 to the power of k plus 1. So that's just case 1 right there. Remember, I'm just listing out these in terms of I now. So I've just rearranged them. So it's 2 to the power of 0 plus 1. 2 to the 1 plus 1. And so on, because this is I minus 1, right? That's all I'm doing. I'm just looking at this cost function. That's all it's saying. So now, what are we going to do? Okay, well, this is just 1 times that is just that, right? So this is just n minus the ceiling of log base 2 of n. Plus, now I'm going to do is, there's a nice property with summations that you can split the summation into 2, because this term is not dependent on that term. So I'm going to split these and then I'm going to add them separately, okay? So I have k is equal to 0 up to the ceiling of log base 2 of n minus 1. Now this is just 2 to the k plus the sum of k is equal to 0 to the ceiling of log base 2 of n minus 1 of 1. So what's happening to that right summation? How many times am I adding 1? Okay, well, it's 0. So 0 is an object here. So I have 0, 1, 2, 3, 4, all the way up to the log base 2 of n ceiling minus 1. How many times is that happening? How many times am I adding 1? Well, it's the ceiling of log base 2 of n minus 1 minus 0 plus 1. Remember, there's that counting rule I brought up. So what is that? That's just the ceiling of log base 2 of n. So that means I can cancel out this with that term. So I have n plus the sum from k is 0 up to the ceiling of log base 2 of n minus 1 up to the power of k. Now, if you know what that looks like, you should know that that is just simply going to be equal to the exponent. I'll leave more details in the notes, but this is just a finite geometric series, which has a nice closed form formula. But I'll simplify it down a little bit, and I'll say that this is 2 to the power of log base 2 of n minus 1, which we've used this before, actually, when we were talking about heaps, actually. So this is just simply just the exponent, the upper limit plus 1, and I just need to minus off that 1 there. Okay? So that's just me using the geometric series, so I'll just mention that here. So this is the finite geometric series, right there. And what do we do with this? Okay, so I should mention that that's the ceiling of log base 2 of n. Now what I'm going to do is I'm going to bound this in a careful way. You would agree with me that if I take log base 2 of n and I raise it, if I take log base 2 of n, round it up, it should be less than or equal to log base 2 of n without the rounding up plus 1, right? That's always going to be at least 1 higher, right? So it should definitely cover my butt. And also I'm going to get rid of this minus 1 here because it's kind of redundant. I'm not going to need it in terms of big O. So what I'm going to do is I'm just going to have n plus, whoops, what am I doing? I assure you this is going to pay off so nicely. So it's going to be strictly, this term is going to be strictly less than 2 to the power of log base 2 of n plus 1. All makes one right there. Well, what is that? Well, it's 2 times that, right? N plus 2 times log base 2 of n. So 2 times log base, 2 to the power of log base 2 of n. Now, if you know your property of logarithms, this base matches the logarithm's base, hence I can switch these two around. Which this, in a fun sense, is actually going to make it so it's n plus 2n, because 2 to the power of log base 2 of n is equal to n raised to the power of 2 log base 2 to the power of log base 2 of 2, which this is equal to 1. So it's n to the 1, which is just n, right? But that's n plus 2n, which is equal to 3n. Whew, that's interesting. So now we know that t of n is at least 3n. It's at least 3n. Therefore, the cost of put in the aggregate method that we're using, the method of put is what? Remember, it's t of n over n, which we already established that t of n is less than 3n, right? So I'm just saying it's less than or equal to 3n. How many operations are we doing? N, which equals 3. Whew. So that's 3 amortized, which is big O of 1 amortized. Woo! Isn't that neat? So it means that in an unsorted array, when we do that insertion in the way in an unsorted array, that resizing really does not occur very often. In fact, it pays off to have a lot of these cheap operations occur. Now, this brings me to an important practical point. So I've established for you that if you use doubling for your array size, that the amortized time is going to be constant for your put operations. So the summary that I want to give you, this is a both practical and theoretically valuable insight, is that geometric growth of an array is a good choice for resizing the array. So that's the big takeaway. Now, oftentimes when resizing arrays, they often talk about growth factors, so-called growth factors. So the growth factor I'm mentioning here is 2. So that was in my scheme was 2. But if you actually work through the mathematics here, you can actually, remember that's the dreaded M word, the mayonnaise, okay? So the growth factor here was 2. Now, if you work through a lot of this analysis, again, with a different logarithmic base and different powers of 2, or different, actually, not just powers of 2, just any power where you're doubling or tripling, quadrupling, or even by some fraction times n, the point is it's multiplicative by something in terms of the original length itself. That this is going to be a good practice. So it's called the growth factor. So for example, in Java, if you use the ArrayList class, at least as up to the time of this video, ArrayList uses 1.5 as its growth factor. So if you resize if you're using an ArrayList in Java, if internally it gets full, what it does is it grows by the growth factor of 1.5. Now, the reason why they pick 1.5 is to conserve memory. So, because doubling your array every single time, there might be trade-offs there. So, this is both theoretically valuable, but it's also a practical consideration. Okay? So, isn't that cool? So, that's how you can use the aggregate method here. Now, I want to ask you a second question. Now, this is the reason why I want to bring this up. So you can see that here, we were able to stave off the expensive costs by instead avoiding the situation of the expensive operation by prolonging it long enough. What happens instead when we talk about resizing by a constant? Which is something that some people might suggest you try doing. So what do I mean by that? So imagine you start off with an array of length 1. And then what you do is you say, okay, every single time I'm going to increase the length of the array by like 5 or 10 or 20. So you might ask, okay, well, what should I do? Should I use this kind of growth factor approach where what we do is we multiply it by the original length of the array by some factor? Or should we add some constant amounts that's appropriate for our application every single time? Now, what I'm going to do with the amortized analysis now is I'm going to show you that this is going to go a little differently, okay? So, how about if we increase the length by a constant? So that's going to be the thing we're going to answer here. So instead, we increase the array's length by a constant, and I'll call it k prime, which is going to be strictly bigger than 0. Now, the great thing is that I've already given you a really nice breakdown of how we can compute the cost. Now, it just takes a small tweak to actually derive this one, believe it or not. Then, the cost C of, well, we'll say C of I, of operation I is, so here I'm just going to write it down. I'll let you think about it, and you'll realize that it's really just, I'm just changing the condition when case 1 occurs. That's really all that's happening. So if I and 1, this happens if I minus 1 is equal to k prime times k for some k greater or equal to 1. So this is case 1. So this is the same idea as before, and this is otherwise. And this is case 2. So notice the only thing I've changed really is just case 1. So notice that case 1 now is by a multiplicative constant. So I have some multiplier to the constant. So I'm going to assume I start off with length 1, and then I kind of fill it up as we go. So anyways, similar to our previous analysis. Similar to our previous analysis. Now, the number of times case 1 occurs is what? Now, I'm going to give it a name. When does it happen? It happens when the length becomes what? What does it become? Whenever I minus 1 equals k prime, 2 times k prime, 3 times k prime, 4 times k prime, and so on. But how many times can that happen for some n, for a number of operations? Well, it happens how many times? Just think about it. Okay, imagine you have n operations that occur. Well, it's going to be something relative to k prime, right? It's going to be n over k prime. How many times can it happen? Well, it's relative to this multiplicative amount, right? It's chunks. Chunks of k prime, how many times over all of them? N over each size of the chunk. But remember, like I said, it's not quite perfect, so I'm going to round it up. Because it's always one higher. Just like I did before. So I rounded up because I is bigger than I minus 1, right? And that's whenever the case occurs. Okay? Is I minus n over k prime as we resize the array whenever. So you'll see that my analysis it's really easy to adapt it. Whenever I minus 1 equals k prime, 2k prime, and so on up to m k prime, where m is what I just said is this. So I'm going to define, so this is going to be defined as m. So wherever you see this, I'm going to use m sometimes to just ease up my analysis, okay? Then, all I'm going to do is I'm going to reuse this over here. Because everything over here should easily translate over here, and you're going to see how badly this goes. So then the total time to perform a sequence of input operations is, this is equal to that. Now, what happens here? It's not going to be any more n minus the log of log base 2 of m with the ceiling. Now it's n minus what? How many times does it occur? M. Happens m times. How many times can the possible resizing occur? It happens when it's k prime, 2k prime, and so on. But notice that my k over there happens for I is 1 and up. But how many times does it happen? It happens m times. What's I in terms of this over here? What is it? It's k. Sorry, k prime times k plus 1. Because remember, I is equal to k prime times k plus 1. Because it was I minus 1 was equal to that, right? So I'm just adding 1 to both sides, okay? See, notice it's just going to fall out really nicely. Now, just to save myself a little bit of space, I'm just going to erase the rest here. Because everything else is going to change up a little bit. Okay, so now there's case 2 and case 1. See, the analysis is going to fall out really nicely here. Because we've set it up really nice and strictly. This is why when you take a more rigid approach, you can actually generalize the analysis technique pretty well. So you can easily extend it. That's why I really want to show you this. Is so that you can see, okay, if I make different choices, the way you construct the cost function actually barely changes. It's a small tweak, okay? Okay, so now we got this. What is this? What is this? This is easy. I have m minus. Now I can use the exact same trick I used before where I split the summation and I end up with how many terms? M terms, because it's 1, 2, 3, 4, all the way up to m. So it's m minus 1 plus 1, which is just m. So I end up with m minus m plus m plus, now remember, this is a constant. So I can pull this out front of the summation. So note I'm skipping some steps here. But hopefully you'll see what I mean if you read this more carefully or try it yourself. So I have k is 1 up to m of what? Of k. Ooh, that's interesting. Do you see that? That's a little interesting. Now this is different than what we had before. What happened before? We ended up with something that fell nicely where it ended up being something linear, right? This is not linear anymore. This is quadratic. So these m's cancel each other out. Then I end up with this. Well, what's that? There's a nice closed form for this. Is the arithmetic series. So I have k prime times that, which is just m times m plus 1 all over 2. But what's m? M was the ceiling of n over k prime. But n is there, right? The point is that n is there. There's nothing canceling in the bottom, right? It's just a constant there. This is k over 2 times that. Which is that this, which is big O of n squared, right? Whoopsie. Therefore, so do you see how the analysis actually spits out what's happening? So you see that before we were able to prolong the expensive operations. They are not being prolonged here at all. In fact, they happen quite frequently. Therefore, put takes how long amortized? How long does it take amortized? It takes big O of n time amortized. Which is much worse, right? This is much worse than we had before. Much worse. So, what do? Would we use this approach in practice? Probably not. That's probably not a good idea. This growth factor-based approach where you pick some factor, and then what you do is you determine whatever makes the most sense practically, depending on your application. But we know from the analysis that the doubling technique works fairly well. The one I've been alluding to for all this time, it works pretty well. In fact, you can use this type of technique, this amortized analysis, to help better reflect when you have a sequence of operations like this. And this is quite frequently something that occurs in data structures. So I really just wanted to show you this so you have an idea. If you ever pick up a paper or something on data structures, if you ever see the word amortized, you need to keep in mind that it's being referred to in a sequence of operations. And it gives you a better reflection of how those operations occur whenever there's a resizable data structure that's underneath it, like an array. Okay? So it's less pessimistic. So just keep that in mind. So if you're looking at the absolute worst case analysis, that is not this. This is a special kind of worst case analysis. Now, aggregate method is quite nice and natural because it falls right out of what you would do. Now, I'm not going to talk about these in this course really, but beyond this course, there are two other well-known amortized analysis techniques. So, there's two of them. One is called the accounting or banker's method. The crickets they're chirping. I don't know if you'll be able to hear them much, but they are definitely kicking around in here in the bunker. So there's two of them. One's called the accounting or banker's method. The other one's called the potential method. So this one's inspired. So the banker's method is inspired by finance or accounting. So in the banker's method, what you do is you assign costs to each of your inexpensive operations and your expensive operations. Okay. So the idea is that what you want to do is you want to imagine, just like what I was saying about taking out a loan. So what you'll do is you apply a charge to your inexpensive operations. You can imagine these like paying small or setting aside a little bit of extra money every single time. So you take that charge and you pay a little extra every single time. That little extra is what you're going to use. You imagine like coins I'm collecting in a piggy bank. And then when an expensive operation occurs, then you pay off whatever might be from your little piggy bank. So you can think of it like paying a regular sum that pops up every once in a while using your savings. Now, the savings is this little extra charge you're going to use. So think of it like taking out a loan. You can use the banker's method to come up with the same type of analysis we are doing here. Same with the potential method. The potential method is inspired by physics. So in this approach, what you do is you formulate a so-called potential function. It's called a potential function. Now, potential method and the potential functions are applicable in several different settings beyond the context of this course. But I'll just mention that it's used in amortized analysis. The idea is you come up with a potential function, and this maps states to your data structure. And then as operations occur, it changes the state of the potential function. And what you do is you measure the cost by the differences of the different states of this function. So what you do is you look at the initial and the final states of this, just like if you're looking at a system, like in physics, where you imagine a potential, like a potential in a force, potential in energy. The same idea applies here. Okay? So that's the idea in the potential method. So these, I'm not going to talk about in this course, but I just want to make sure you're aware of them, okay? So what we're going to do is I'm going to spend the last few minutes talking about the next topic, and then we'll come back to it next time, okay? Okay, so the last thing we're going to talk about today, we're going to revisit dictionaries. We're going to talk about the Ordered Dictionary ADT. So we've talked about dictionaries before. Remember, they have records, and they had a whole set of operations, right? So what does it do? It allows us to store a collection of records records. Remember, we're talking about records again. Remember, the keys are unique here. Records of the form key data. Remember the pairs. Where, now this is where it changes. Where the key attributes come from a total order. Now, this should sound rather familiar to you because we talked about this actually when we were talking priority queues from a total order. So, what do I mean by this? Given any two keys, K and K prime, we can always determine if K is equal to K prime, K is less than K prime, or K is bigger than K prime. So you can define these, so you can either be equal, come before, or come after, okay? So, for example, total orders are defined over integers. So integers, of course, have this property. Characters also have this property. Strings also have this property. You can also define your own total ordering. Usually, when you compare two objects using a comparator or have comparable objects, this is something that you're looking for. So, that being said, what we're going to do is I'm going to lay out some operations here, so just give me a moment. I'm going to write them down, then I'm going to describe them to you, okay? Okay, so I've just written out the operations. So, an ordered dictionary has the operations you're familiar with a dictionary, but in addition, it typically has some of these other ones here. So the first one is smallest, so you just return the one with the smallest key. Now remember, it is a dictionary, so there is a unique smallest key in some record. Likewise, there's largest. The same idea, except you're just going to return the largest key. The record with the largest key. See, I'm getting it. I like talking about this. Predecessor, you're just going to return. Now this is where it gets a little bit weird. Predecessor returns the largest key less than k. So you give me some value k, and you're going to give me the record that is the largest key that is less than that value. You'll see more of this kind of thing when we start talking about trees again. And its successor, we're going to return the record with the smallest key, but it's larger or greater than k. Okay? So what we're going to do is we're going to be considering this ordered dictionary when we talk about the next topic, which is going to be binary search trees. Okay? So thank you very much, and have yourself a beautiful day. I'll see you later.